Okay, here's another slightly more complicated algebra functions problems. This is such a common algebra functions example or class of problem that we call this one a difference quotient. And we'll talk a little bit about why it's called a difference quotient here in a minute. But if I want to just evaluate this, let's write down what is my f of x plus h here over to the side. Well, I'm just replacing my dummy variable x with x plus h every place I see it. And so I have x plus h squared plus 1. Okay, well, let's use that to assemble this. I've got x plus h squared plus 1 minus, and then that's my f of x. That's going to be my x squared plus 1 all divided by h. Well, x plus h squared, that's a binomial squared, and so that's going to be x squared plus 2xh plus h squared minus x squared minus 1 all divided by h. I have an x squared and a minus x squared. Oh, I messed up. Before that minus, there was a plus 1 that I didn't copy down. All right, now there's a plus 1 and a minus 1. And what am I left with? I'm left with 2xh plus h squared over h. I can factor an h out of that numerator, and I'm left with h times 2x plus h divided by h. My h is canceled because h divided by h is 1. 1 times the 2x plus h is the 2x plus h. And I'm left with 2x plus h for my final answer. What's interesting about this difference quotient? What's interesting here is I sort of have two function outputs, right? So if I go down here and I just write down the difference quotient, that's going to be that d of x equals, and I said f of x plus h minus f of x divided by h. Well, I'm going to change my colors around a little bit. I'm going to change that to a purple. And I'm going to change my f of x plus h to a blue. And we'll leave the h down there, and the denominator is black. What do I really have in the blue and purple values? Well, f of x, that's the output of the function f, right? Evaluated at x. Well, an output of a function, that's like a y value. And so if I were to sketch some unknown function shape here, and I'm gonna cheat my axis over just to kind of just look at one quadrant here. So I'm just gonna look at the upper right quadrant. And so if I have my function shape here, well, my f of x, that's going to be this x value, and then the y value associated with that, that's going to be my f of x, right? Now, this x plus h, that is just some value h further along the x-axis, right? And f of x plus h is whatever y value is associated with that point, right? And so literally, my h is that horizontal distance between the 2 points. And so my h is that distance. And then this distance between the two y values is f of x plus h minus f of x. that looks an awful lot like a change in y, right? Because that is my change in y, and that is my change in x. And so what we're really saying is that we've found the slope of the line that passes through those 2 points. And the slope of the line that passes through those 2 points is this difference quotient. And so this difference quotient that we're finding is nothing more than a linear slope. Now, I can't get you this close to a concept without actually mentioning the way we leverage this concept in the future. This is not part of an algebra class. This is kind of your first steps into a larger world that is calculus. But so this won't be anything that we test over in this algebra class. But I can't get you this close to it without telling you that you're like right next to doing calculus. The whole idea of our first calculus concept is that we've talked about rates of change of linear functions before. That was our slope. But what if we could figure out what the rate of change of a function was at every instant along that function? So what if I could, put in an x value here and find out what the rate of change of that function was at that instant, what the instantaneous slope of that function was? Well, that's what we're on our way to figuring out here, because this is an approximation of the slope of that function for some finite distance h here, right? But what if I shrunk that h down and made that h smaller and smaller and smaller and smaller? Well, as that line got closer and as those 2 points got closer and closer and closer together, the line that connected them, the slope of the line that connected them, would become closer and closer and closer to the slope of the tangent line that passes through that point as h gets really, really, really tiny. Now, h cannot equal 0. That would be a discontinuity. Even if we can cancel h out, h cannot equal 0. That would be a removable discontinuity. But we can kind of say, what if h could equal 0 if we can cancel the h out? And that what if is the basis for our derivative. It's a process called a limit. We're taking the limit as h goes to 0 of this difference quotient. And that finds us our instantaneous slope, because it lets this distance between these 2 points become practically 0, and gives us the value of what the slope would be if it existed there. Okay, well, for that to work out, the h value will have to cancel out, because I can't evaluate an h of 0. Well, the h value did cancel out, and now I can evaluate an h of 0, and I find out that function is just 2x. And so the big reveal here is that the function 2x contains every single slope of the function x squared plus 1. And there's a lot more to it than that. Otherwise we wouldn't have a whole class dedicated to Calculus 1. So there's a lot more to the story than that, but that's kind of like the big reveal behind this calculation is our whole, hey, we've done all this algebra, now let h equal 0. And when h equals 0, then we found that derivative of this function is 2x. And so that's the part that we're not asking you to do right now. but conceptually, that's what we're right next to when we get this answer. Right now, you're just responsible for finding that 2x plus h, for being able to evaluate this difference quotient and find the 2x plus h. But to be honest, the algebra of this is mechanically the hard part of finding these derivatives. Conceptually, it's not the hard part of finding these derivatives. Conceptually, the hard part is conceiving of this instantaneous slope at this one point. But mechanically, the hard part of finding these derivatives is actually evaluating this difference quotient accurately. And so you're right next to doing calculus, even though you're in an algebra class. That's either wonderful or terrifying, depending on your perspective. I hope it's wonderful. Hope that helps us as we're doing these algebra functions problems.